Yeah, I wish I could be with you. Hopefully next year it will be really nice to then share with you face to face all these presentations and advancements we have been doing over this project and some others. And really thrilled that you have all these questions for us, for Konstantinos on caipirinha and what we have been doing on the use of direct ammonia. Can you see my presentation? I'm putting it into presentation mode now.
Perfect.
Excellent. Okay. So again, thrilled to see that there have been lots of questions about what we have been doing. And I can expand on many of the points that were raised by Konstantinos, particularly on the technicalities of using combustion. So this is a program that is called Caipirinha, as mentioned by him, and that we got funded by European Union. And the whole rationale behind it is that we can use directly ammonia for many different applications. So this is just a brief introduction for those that like reading. This is some of my CV. But the reason for it is if you don't like it, again, you can listen to the story on how we came across the use of ammonia. This goes back 14 years ago when one day before Christmas, Siemens showed up and said, we want to burn ammonia. We didn't understand what they wanted at the time, and I decided to take the challenge. Why not? Wanted to find something new and then give it a go with ammonia. We thought at the beginning that it was just a simple project, but eventually we managed to then find out there were many things going on, particularly in Japan, where things were happening at industrial scale. People were doing very interesting research. And eventually, we managed to then get on the train and develop many different applications. One being this program, Caipirinha, which I'm very proud to say is the first one of its type worldwide. So again, thinking about Japanese being ahead of us 5 years in this subject of ammonia combustion, when it comes to then the integration of both liquid and plasmas, we are the first ones in the field, which is again very exciting and very nice. So along those lines, why we want to use ammonia, this we have been talking about for ages, was discussed during probably some of the conversations this morning, and again is to provide some backup power to the intermittency that we suffer because of the renewable energy sources that we're going to be tapping into. Since we have wind, we have solar, we need to then have some way of reliable storage that we can use to provide and support the intermittency of these systems. One of those cases that was critical here, for example, in the UK, was around 5 years ago. Just before COVID, 7 years ago. And when we were running around 50% wind power, something happened with the wind. It stopped blowing. There were problems with some of the wind farms, and eventually we lost power that were feeding around 1 million people in the Midlands, then showing that we needed to have more resilience on these type of systems, therefore trying to then bring into the agenda more diversified storage medium. So as part of some of the programs we've had, we have been dealing with different industrial partners, some of them that Siemens were looking into different strategies for storage energy. And as you can see, we have all these different type of vectors. This is an 8 years old map that hasn't changed much, but it still shows how batteries, flywheel storage, supercapacitors, pump hydro, and thermomechanical storage play a big role in all this agenda. Now, one of the things that is interesting is to see how all these different technologies span for different storage times and also power ratios. One of the different media that is actually quite versatile is the use of chemicals, but in the case of methane and also hydrogen and ammonia. And the reason for that is that not only we know how to use chemicals because we have been doing it for centuries, but also we can then use some of these vectors that we have moved around for ages. In the case of ammonia, for example, it's been around 180 years that we have been using it for fertilizing applications, beginning of last century when it just became industrialized and eventually just boosting a third of the population worldwide. It's again one of the main reasons because ammonia presents a very interesting case when it comes to certain applications. So looking into some of the analysis done by the Hydrogen Council, they evaluated the availability of different resources, wind and solar mainly, and how we could tap into those. Similarly, they compare what would be these resources still tap into natural gas reservoirs that we can then access. But as you can see from the two, the green being the renewables, the blue being the natural gas resources, the latter is less diversified and just localized in some areas across the world, whereas the other one is everywhere essentially. So what they did was to, as part of this, analyze what would be the case of bringing hydrogen in different ways and thinking about long distance distribution from locations where they would produce it in larger scales and eventually deploy it in locations that require it because of the industrial size. So this was an analysis done from Chile to the US, Saudi Arabia or Middle East to Europe, and then Australia to Japan. And comparing the different vectors that they had at hand, ammonia, liquefied hydrogen, and liquid organic hydrogen carriers, they figure out that the cost from the clean production site to the final destination at port would be relatively the same between 3.2 to 4.4 dollars per kilogram hydrogen being moved. However, one of the things that appears and very interesting is a big component of all this cost is the cracking that comes from the delivery of this ammonia to hydrogen. Therefore, if we reduce that component, we're talking about almost a third of the total costs, and ammonia being that the situation of long distance mobility being the best scenario in terms of economics. Therefore, again, just like places the question, can we burn ammonia efficiently and directly into these combustion systems? So this is some work that we have been doing in collaboration with many other universities, Newcastle, Nottingham, Bath, to evaluate where we see this ammonia stream going into. And we know that there will be many scenarios where hydrogen will be the king. For example, when we're talking about city deployments and small distance, short distance distribution, immediate utilization, it is when hydrogen will be ruling out over some other molecules. However, when it comes to long distance, and again, going back to locations that are isolated, then ammonia, we see it as the best option. So that comes as marine, potentially propulsion, as I'll raise it now in one of the questions just brought up to the chat, and obviously rural applications where we have disconnected locations. For example, here in the UK and as well spread across Europe, there are many farms or small communities that still rely on propane or other chemicals because the connectivity via electric grids or gas networks is impossible. It's simply too expensive. So therefore, they've been relying on these fuels for decades. And that is not going to change in the short term. So therefore, making ammonia for these particular situations, very good option. So one of the big problems that we face is how to burn ammonia. And well, we have different alternatives. So we can then provide for some doping that can boost its reactivity. We can then use it directly. We can then have it in gaseous form, liquid, etc. If you compare between all the different fuels that we have in this table, the part that is the most concerning is actually with the lower heating value that we might have similar between ammonia and methanol is actually the laminar burning velocity, how fast it can burn, and the ignition energy. If you see between all the different molecules that we got in here, the case of ammonia is a few hundred times higher than the case of hydrogen for ignition energy. Similarly, when it comes to what is its laminar burning velocity, its burning velocity, we're talking as well about a few hundred times lower than the hydrogen, then making it very difficult to burn when it comes to its direct injection. So either again, you go with the case of having some doping agent like hydrogen that can be obtained via partial cracking of the ammonia. You can mix it with natural gas and that way provide for a transition from natural gas systems, propane, as I'll show you later, or even some other alcohols or fossil-based liquids like gasoline or diesel. So this is one of the big complex components that we got when we burn in ammonia. So therefore, what we have been doing is looking into some of the fundamentals on how to do so. And from studies that we have done on reaction mechanisms, laminar burning and turbulent burning velocity analysis, detonation, porous media, systems, again, that have a great novelty, we have as well jumped into the field of plasmas. Why plasmas? Well, a few years ago, and around 2018-17, there were a few documents where universities in Germany started looking into the use of plasmas for the combustion of hydrogen. And it was very interesting because going back to Constantino's point, one of the things that the plasmas tend to do is to create radicals. So if you have all these radicals that are just about to or ready to be born, then once that you get to the burning zone, they start mixing with the oxygen immediately and then reduce the time of reaction. Similarly, what they do is they are radicals that are more strategic in that recombination with the oxygen and therefore produce the final molecule, in this case water, when they were doing the analysis with hydrogen, instead of producing nitrogen oxides. So that was something that spurred imagination and eventually led to some of the groups in Georgia Tech in the US to then characterize the first ammonia plasma system. And it was very interesting because once that they started using it, what they found out was that the stability improved, the flame got better, and also the emissions profiles in terms of nitrogen oxides that we tend to have from ammonia combustion went down drastically. So as part of that program, we start working with our partners in Birmingham and also Oxford, and then delivering some analysis via numerical modeling. And one of the things that we found was that depending on the amount of energy that we put it into the plasmas, the type of concentration that we have between the air and fuel mixture, then that profile would change drastically. So there were many questions to be answered yet, and then we decided to then carry on with our program. And that's when Konstantinos talked to us and said, guys, we are doing plasmas. We've heard that ammonia can be born this way, and why not giving it a go? And at the time, we actually were working with KAUST, a very important combustion institute, probably many of you know about, and they were already looking into this potential idea. So what we started doing at the time was looking into the production of some plasma systems, something that is a gliding arc, simple type of system, similar to those that you can see in Frankenstein movies. And then from that, give it a go, hope for the best, and then test some of our burners using this technique. And surprisingly, what we found out was that first, the stability improved. Second, nitrogen oxides as well were improved, even in the worst case scenarios where you have very high NOxes, like is the case when you have an excess of oxygen in the field. And with that, we saw this big potential of using plasma systems, using our units. One of the things that we saw as a big potential, and going back to one of the questions is like, how could we use, or if it's any potential of actually using this for propulsion systems in aerospace? I honestly believe that this is the only way to actually have ammonia in aerospace applications. Because one of the big issues that we would have otherwise is to then have to prepare the fuel, gasify it, and for that having evaporators that will be just too complex and heavy to have in an aerospace application. However, if the plasma systems are miniaturized and just small enough to then provide for that plasma to be created, and we manage to then get this ammonia injection via liquid done straight away, then there's nothing stopping us in putting these type of systems straight into aerospace applications. So therefore, we decided to join Konstantino's proposal and thought, okay, this proposal looks very good, and let's give it a go. But then at the time, one of the big questions was, okay, so we can then bring plasmas. People have done it already with gaseous injection. What would happen if we decide to go with liquid, just again, to prepare it as one of those concepts for marine and aerospace applications? And as part of that, so some of the studies that have been ongoing, we included, they analyze what happens when you have ammonia being injected. And depending on that pressure, going back to the pressure, what you could have is that if the pressures in the atmosphere that you're injecting the system are not high enough, you might have flashing conditions. So you will have then the spray that eventually will vaporize, but because it's just cold enough and then reaches that point of a balance between the liquid and the vapor, it will start producing liquid again. So you end up with liquid droplets in such system. Whereas in the cases where you have higher pressures in your atmosphere, then you reach only the spray atomization as you will have it in any other application being liquid. So therefore, at lower pressure, that causes a lot of problems that we wanted to exploit in a way that would give us something new and interesting. So from that, we jump on the program and decided to then use a system that at lower atmospheric pressures will produce from a high pressurized system, around 20-25 bar injection, a mist that is to be produced first in a atomization form, liquid, then it will vaporize partially, and then eventually parts of that will convert back into droplets or very small droplets for a system to take into. And as part of that, thinking how we can then integrate that into this plasmas concept, then add the plasmas for the creation of the radicals at the front where all this is happening. So with that, we'll generate enough radicals to then start the reaction, and then at the same time, make the best use of this change in phase that we'll experience using the liquid ammonia. Plus, again, reduction in retrofitting that many of the systems under these conditions might have. So as part of that, we have not only the experimental campaign with confinements, droplet generation, morphology, and angle analysis, but also we have the work from Lund that is looking into the reaction mechanisms that will require us to have some CFD modeling at the highest accuracy and validation. So it's a very interesting program that combines experimental, fundamental, and modeling characteristics on how to deliver these type of systems using nano repetition rates plasmas. And I think this goes back to one of the questions, why nano repetition rates? Well, as I said, we did gliding arc, and that worked nicely. But the problem with that is that it doesn't approach the entire field for the production of these radicals. We have something that is producing the plasmas at a 2D through a 2D profile using advanced systems. We might end up with a very nice homogeneous profile of radical formation, therefore combustion stability. And in some of the cases, for example, some of the things that Konstantinos is doing, looking into different geometries to maximize cases of sharing flows, fluid dynamics, and coherent structures that happen in these type of systems that we can use as part of the component of stabilization of the final flame. So with that, we got a system that looks like this, laws of health and safety. I'll show you the next slide, because we are bringing now liquid plus plasmas high voltage systems into the lab, and all that being pressurized at, as I said, 20 bar pressure delivery system. So with that, we are measuring voltage, current, pressure, so we are able to define what is the energy that we got from the plasmas. And one of the things that I said we have been doing is all this health and safety. This is just an example of a 20 pages long analysis we had to do to be compliant with the laboratory requirements, where we had to do analysis of the flash fraction that we might generate in case of a leak from the liquid injection system, Hasopin, ATEX rating, etc., that have been again extenuating, but now we're in that stage where we got everything ready and the system ready to start running. So with that, we have managed to then get the first analysis being done using this plasma system. You can then see, well, one of the things that we are doing is using ammonia directly, all gaseous at this stage, because we are now in the final commissioning, 95% of the liquid line, and is purely ammonia. And depending on the amount of premixing that we do, so we are doing pure ammonia, and then eventually we bring the air into the combustion zone, or we just premixing with some preliminary air ammonia conditions. We have different profiles of the species radical formation that we can have in such a system. NH2 star, OH star, and you can see as well the stability increases, the map enhancements, the orange zone that you have on top of the gray one is how we have improved now operability of the system. And as I said, thanks to all these measurements that we are doing, we can estimate that for this particular system using gaseous, we are actually using around 3% of the flame power outputs that we're generating, which is essentially nothing. We initially thought that it was going to be massive because of the amount of high voltage that we were going to require, but it's actually the other way around. It's a very low amount of energy that we're requiring because of these high repetition, high intensive plasmas that we are just generating in a very thin two-layer layout. So with that, just mentioning about some other projects and how we're moving into these for more practical applications, looking into the future. We are already working on an engine, a boiler system that is going to deliver around 1 megawatt power. It's already been tested at 0.5 megawatt and is already generating steam that I'll show you here in this video. So this has been taken just a week ago, and this is the kind of systems where we can then implement all these caipirinha concepts. So right now, we're bringing the ammonia gaseous, but the idea is to as well evaluate its use via plasmas and directly to injection to then provide for that power that we are generating. So these are some of the applications where we see future. Some of the systems that we are using via this way, again, on the design of swirl combustors, are allowing us to then produce power at that scale, 0.5 megawatt and almost a megawatt with negligible N2O, NO2, and hydrogen measurements, with almost 25 or 50 parts per million of onboard ammonia and nitrogen oxides, which is, again, very good, super low emissions. So with that, I'd like to conclude. These are some of the applications where we see loads of potential, power generation, aerospace, again, being caipirinha, that concept that we are trying to bring to this field, power generation at larger scale, similar to what Mitsubishi is doing, liquid formation, and some other aspects of the recovery of ammonia from marine systems. Collaborations that we got ongoing, lots of work with different universities, so anyone interested, please let us know. We're always happy to collaborate and work with partners across Europe and the world. And these are some of the things that we have created, a journal on the subject, a few books. And if you're interested in presenting all this fascinating information that you've been sharing, we have a symposium in Chile in September that will be on every aspect of ammonia energy, from the production to the storage, distribution, and utilization of the concept. So with that, just to conclude, that ammonia can be used to store energy for long distance and long periods of time. The low reactivity requires additional methods for combustion improvement, such as plasma, that can be a great solution for mobile applications. In this case, we're thinking again, internal combustion engines, and as I've said, propulsion systems for aerospace. And finally, ammonia in rural locations, we believe as well, is where we have a great potential, because people in those areas, they are used to fertilizers, used to ammonia, and as long as we have the right regulations, something that is not toxic, high toxically, that can be a problem for health and safety, and these communities are the way to move on a commercial solution. So with that, thank you very much, and I don't know if there's any question.
Thank you very much, Augustin. Any question? Everything was very clear. I have a question about the energy use. You mentioned 3% of the energy generated by the combustor then. And before there was a similar question. Is this energy use is just the pulse, or is the total electricity that you put in the system?
So it is the total energy that, yeah, so it is the total energy that we use to produce the pulse. So for example, controllers or systems that are feeding the lines, yes, we don't take them into account. We could be able to do that. And I think one of the components that we got in caipirinha as part of the control integration is to then take that into account. But yes, this one is just for the pulse.
Yeah. Okay. Other questions? I have another question. The system that you do in Caipirinha and the system that you show in the combustor of 1 megawatt or half a megawatt are similar.
Yes, so
I'm referring to the scale up of Caipirinha. So
yeah, so the one that we got a 0.5 megawatt is a furnace that we got downstairs, and that one is being fed by gaseous ammonia. So a regular swirling flow, a combustor at that scale, and the one that we got at 1 megawatt is a boiler that is generated steam. Now the relevance to Caipirinha is that what we're looking at is using these plasma systems with liquid injection directly without having to employ an evaporator. To give you an idea, the evaporator that we got for the 0.5 megawatt, well, for the 0.5 megawatt, is about 1 meters and 80 centimeters high, with all this infrastructure that requires the evaporator and the power that is needed to bring it to gaseous form. So it's a big consumption of energy and also infrastructure. If we were able to then inject directly the ammonia into the system, that will save us not only the money on that, but also the energy consumption that these evaporators require. That's what the principle we're after is trying to do. Japan in IHI systems, gas turbines, they are evaluating already liquid injection of ammonia. Problem is the nitrogen oxides that they produce, because the fuel is less prone to being combusted, and therefore produces higher inefficiencies, which is again one of the issues of what they're experiencing now. And as I know, just last week, the teams of IHI, Kyushu, and Tohoku, they got funded for a plasma liquid injection system just because of that.
thank you very much. No other question for Augustin? I have a question that is more for the presentation, because we share the presentations of this workshop. So if you can send us the slides, then we will share with all the participants. Oh yeah, there is a question. Sorry.
Hi, Augustin, Jimmy Faria. Nice to see you. Very nice presentation. I was intrigued by your comments and your final slide on the airplanes or aerospace, you said. Could you maybe elaborate a little bit more? I mean, it's a heavily regulated type of sector. So could you maybe tell us a little bit more about the thresholds and the kind of complications that you foresee for ammonia as a fuel for that?
Yeah, absolutely, Jimmy. No, it's always nice to hear you, and hopefully we can see each other very soon. It is a fascinating area, and actually, Boeing and NASA are working with the University of Central Florida on the concept. And all has been secrecy. They are going to present some results in Chile from the work that they have been doing. So, for example, in our case, the way that we see it is using that plasma system to then provide us for that feasibility. So overall, is that you have that ammonia, as I've said, is very dull, it's very difficult to burn, and if we compare it to then kerosene, is one of the big issues that we will have. We know that the amount of fuel that you require for, say, jet fuel compared to ammonia will give you around 45% of the flight potential that kerosene will give you. So again, thinking about 1,000 miles distance, the case of ammonia will only get you around 450 miles. But still, it's a little bit higher, a bit longer than the case of hydrogen, that because of its energy density, it will only get you to around 350 miles distance. So therefore, ammonia presents a very interesting case. Again, the problem is its reactivity. So with the system of plasmas, what we're trying to do is actually cut back on that issue and boost the reactivity by the formation of these radicals at the front of your injector. So if that is possible, then what that means is, just as Konstantinos was saying, we're going to form all of these radicals that essentially is kind of pre-cracking, but before actually getting to crack and react and form hydrogen and nitrogen separately, it will form just radicals that are just ready to start the reaction. And with that increase, that reactivity that we require for the blend, If that was the case, then direct ammonia injection could be a feasible solution to have these power systems, because again, it doesn't require the evaporator, can then be done exactly at the injection point, and with that provide for the reactivity that the molecule is missing. Now, one of the things to then get to that point, obviously, will be to then have all these plasma systems be reduced. So we need something that is small enough. However, that might not be a big issue. Again, thinking about electronics and how things are moving so fast in that field, it's, again, a potential, and the only way that I see this happening. Yeah.
Thank you very much, Augustin. Thank you again, the speaker. And Augustin, there are a couple of questions in the chat, if you can answer in the chat. And in the chat, there is also mentioning of Paraguay, I think was, right? As a potential place to do green ammonia. So perhaps in our projects, we should also check at that. Thank you very much. We have now a coffee break, and we will start at 4 o'clock again. Thank you.
Thank you, everyone. Any doubts or any questions? I'll be answering here in the chat. So yes, please keep them coming, and I'll just answering them now.
Thank you very much. I think we have to restart. Some people are still taking coffees. They are already connected online. You don't hear? Can you hear online?
Yes.
Yes, they can. Okay, thank you very much. So now we can continue with the last two presentations of today of the workshop. And the next one is from one coordinator of a project. Faster is Jimmy Faria. I always said Jimmy Faria, but now it's okay as well. So Jimmy is a professor at the University of Twente. He's expert in catalyst and processes for sustainable carbon and nitrogen. He had a BD project when you started in Twente, and now he's also obviously a coordinator also of Faster, and he also coordinates activities in the Netherlands about nitrogen fixation on nitrogen chemistry in general, I would say. So Jimmy, the floor is yours.
Thank you very much for the kind introduction, Fausto, and also for organizing such a very nice event. It's fantastic. I think we really appreciate the amount of effort and putting into making this happen. For me, it's also a privilege to share with you some of the let's say initial results and also kind of the thoughts that go behind the Faster project. But in addition to that, I have to say I'm going to be talking also of another project that it's on the ammonia cracking and some really exciting results that we got on that side that are not necessarily related to the Faster project. So these are going to be two parts of my presentation. The underlying motivation for using ammonia as energy storage material was already discussed in the panel discussion. Is the seasonal energy storage. So for example, these are calculations done in Madrid, for example. If you take the solar radiation and you calculate how much energy you would generate, you see that there is a mismatch between your energy production and energy utilization. So that's what you see, the energy deficit on the sides. So can we use ammonia to move that energy from the summer into the winter periods? And for that, when you look at the different, let's say, possibilities, this is the same plot that Augustin was showing, but it's in a different, slightly format. You see chemical energy vectors are One of those materials that you have sufficiently large energy capacity for, let's say, installed capacity for production, and you can also make it and transport it for periods of weeks and months. So in the case of the Faria project, we are aiming at not necessarily gigawatt scale, but as I said before, we're looking into decentralized production. So megawatt scale generation of your ammonia storage and then usage for later energy generation. Now, the concept behind this activity stems from a lot of work that we have done in the group, trying to understand how we could use ammonia as a seasonal energy storage to buffer peaks of energy production. And we study this primarily for remote locations, so islands, remote locations in South Africa. We also are currently studying the case of Morocco as well, where you can think of using renewables to generate your water and also energy for a community, but you can also use it as a fertilizer. So the ammonia serves as a kind of water energy food nexus in this approach. You generate the ammonia during the peak season of energy generation, and then you utilize it when you don't have it. So that's the underlying idea. And after many, many years working on this, we finally got the Faria project funded, which then tries to leverage this concept. And the idea is that essentially you just try to reduce the levelized cost of your energy using the ammonia as an energy. Now, as I was mentioned by Fausto, I'm a catalysis person. I like to understand things starting from the conversion step. And when you look at the synthesis versus decomposition, there is something that strikes you immediately. And this is already mentioned by Faria many years ago. The catalyst that is very active for the synthesis of ammonia cannot do the ammonia decomposition. And so you cannot apply the micro-reversibility principle to use the same material for both the steps. You actually need two different materials for that. That has to do with the Bronsted-Van-Polanyi relationship. So how catalysts that interact very strongly on one way in the table, they will not do it so well in the other side. Now, for the particular case of today, we're going to be looking at two steps. One is, of course, the ammonia synthesis, where the rate limiting step is now the dissociation of your nitrogen. Second part of the talk will be about how can we do ammonia cracking. So that's what I have to do. We're going to be looking at how to activate nitrogen-nitrogen bonds and how to activate nitrogen-hydrogen bonds. Maybe I hope that my talk is not too
I will stop you otherwise.
Yeah, technical or so. But the main idea for the project phase is how can we make it flexible, how we can downscale it to megawatt sizes. And for that, this is a very nice work. You see that if you start lowering the scale of the process, the energy footprint of your ammonia kind of goes up exponentially. So how can we go around this issue of down scalability of conventional Haber-Bosch coupled to electrolyzer? And so that's where the Faria project comes along. And the idea there is that we use absorption enhanced Haber-Bosch coupled to a low temperature ammonia synthesis catalyst. So these two options essentially lower your capex, lower your opex, because you don't need to go to very high pressures, and therefore you don't have such a large energy loss. All right. So the Faria project is all about ammonia synthesis. That's what I will discuss in the first part of the lecture. The underlying project objective is to develop this flexible platform that can convert ammonia. The objective target here is TRL4. And as I said earlier, we try to address a number of societal and technical challenges for low-cost seasonal energy storage solutions. That's the main underlying target. And the idea eventually is that we can have a platform where you can combine this water energy food nexus, that can be deployed in either rural areas or islands and so on. And for that, we have a number of components that built towards these targets that go from fundamental DFT calculations of which materials can do these type of reactions to the reactor and catalyst structuring. So these are the sort of technological innovations that we bring in. And this is a snapshot of the consortium just so that you know, we have also certs. It's really nice to have colleagues of certs here as well. Politecnico de Milano and Umicore are helping us with the catalyst structuring, someone with whom Fausto also have had strong cooperations. And then we have LCE doing the life cycle assessment and system engineering analysis. Proton Ventures, a company here in the Netherlands, doing together with Suster, another company here in the Netherlands, the reactor prototyping. And then Cardiff and Twente working on the catalyst development. And at the end of the pipeline, we have a company, WinGD, that used to be Wärtsilä, but now they have sort of changed their name for some of the things that they do to WinGD, and they are the sort of manufacturers of these two-stroke engines and so on for ammonia to power units. All right, so I'm going to briefly talk about these few key innovations. The first one starts with the making of the catalyst. This cartoon, what it illustrates, it's what is called, in this case, a metal nitride containing a metal cluster. And the idea is that you try to leverage what's called a Marshman-Kremelin process, where your hydrogen starts to dissociate on the metal side. It reacts with nitrogen that is on the metal nitride at the interface, generates a vacancy by evolving ammonia. Once you have that vacancy is a strongly, let's say, nucleophilic species, so it can actually, attack the nitrogen, and in that way you can now form sort of a regeneration of the metal nitride and you close the chemical loop. Yeah, and this cycle has been demonstrated by the group of Osono in Japan, where they have shown a conversion, at very, very mild temperatures and pressures. The general idea is that this vacancy, when it is formed, it injects electron density in your metal, and that changes the filling of the D states on the metal surface, which makes it very, very reactive. Now, one of the limitations in this picture is a metal nitrides. In this particular case, things like cereal lanthanum nitrides, they are extremely sensitive to oxygen, and they will essentially not be scalable. So the objective of the FASA projects is to move away from metal nitrides and use mixtures of materials, so things like metal oxonitrides, and that can allow us to operate these catalysts in the presence of things like water and ppms of oxygen and so on and so forth. That's a very, very important innovation. We have a few results on this as well later on. The second innovation relates to the development of the catalyst structure. In this case, we have the Politecnico di Milano, who has worked very extensively on developing these 3D printed structures that you can now use as thermal conductors, but also as catalyst support. And so you can either coat them, or you can just use them as a scaffold to transport the heat via conduction into your reactor. The third innovation, that's the last one, it's all about the high fidelity modeling of this process if you are going into dynamic operation. With that, at the University of Twente, we're going to be working on bringing physics-based multi-scale modeling of the kinetics that we can get in our labs, and then couple that with heat and mass transport models, and eventually with the Aspen process modeling, so that we can get techno-economic assessment and also help our colleagues with the life cycle assessment. And this is very important because we have to have this in dynamic, and modeling these processes in dynamic is not trivial. And so creating just, let's say, steady state operation models is not enough. We have to be able to model the dynamics. So for that, we need data from the pilot system. So these are the three key innovations that we are working on the FASA project. And now in the next few slides, I'd like to tell you a bit about what the catalyst developments are, to the extent I can. So we started with our colleagues in Cardiff. They look at different materials, essentially trying to understand what are the energetics for the nitrogen vacancy formation on different metal nitrides. And as of, let's say, December, they have explored more than 140 different surfaces. So this is really screening the periodic table to a great extent. And essentially, right now, they have calculated these oxygen, nitrogen vacancies formation for more than 70 of these 140 values. So they have now created a library. They feed that information to us. We go to the lab and we start making materials. Now, what you see here, I cannot tell you exactly what ABC are. I can just tell you that there are metal nitrides that contain certain concentration of oxygen, which means that they will be scalable. We don't have to work in a glove box. We don't have to work in an inert environment for their manufacturing, which means that they will be much easier to scale down. And what you see here is a temperature program reduction. So this is the first step in the catalytic cycle. And what you see at this plot is the temperature at the normalized intensity of the ammonia peak. And this is in the absence of any metal function. It's just a metal nitride, metal oxonitride. And you see that there is evolution of ammonia for conditions that are otherwise very difficult to activate nitrogen bonds. In this case, this ammonia actually is or nitrogen oxygen vacancies that are being generated. All right, by hydrogen. You don't have a hydrogen dissociation function here. Yeah? So that's a very, very interesting, very, very interesting point. Now, if you add a metal functionality, which I cannot tell you also exactly which metal it is or anything about its size, I'm sorry about that. You now can actually activate a much larger fraction of your metal nitride and evolving a greater amount of ammonia. And the temperatures also shift towards slightly lower volumes. We have actually newer materials that I'm not showing you today that show even much, a larger concentration of ammonia evolution. Now you can take that data, and what you see here, generally speaking, is that you have three different types of temperatures, and you see the sort of region where we're interested on is the temperatures that go all the way to maybe 300 degrees C at most. And so we're interested on this plot over here, and you see that now we have a formulation that is very promising for such an operation window. At 280 degrees C and about maybe 50 bars of pressure is the idea that we have for this. So, we have time. Okay, good. So as you can see, during this first year of the project, we have been very busy in trying to create materials that can do this job, and we have some very good leads at the moment. Now the next period is going to be about doing the full kinetics, because this is just a temperature program reduction experiment. So we have to now test this under reaction conditions and see what is then the turnover frequency of these materials and benchmark them against conventional ruthenium-based catalysts and also iron-based catalysts. And these results are actually quite promising. Very well. Summary, we have new formulations. We're trying to complete the catalytic cycles, as I said, and in the next few months, we're going to be busy with completing the testing facilities and conducting experiments that can facilitate the connection with the DFT work that Cardiff is doing. Very well. So those are the leads. I can tell you about the FASTER part. The second part of my lecture, which I'm also very excited to share with you, has nothing to do with FASTER. FASTER, we're going to do ammonia cracking, but in a very, very different way. Not that the proof of concept I'm going to show you has no implications there, but this is something very different. This is a project funded by the US Navy. They came to us with a very specific question: can we do ammonia cracking? And we came up with a few ideas, and they selected this, which is called dynamic catalytic cracking. And the idea here is that if you have a conventional fired ammonia cracker, this is not my data, so please, colleagues in the audience, forgive me, this is not right. You get these kinds of specific energy inputs in the order of 10 kilowatt hour per kilogram of hydrogen. And in principle, if you get rid of the very high temperatures that you need for these processes, this is at 800, 900 degrees C, you could lower the overall heat losses in the system by about 27%. So these are not my estimation. This is just from that paper that you see. And the beauty of it is that if you now couple this to electrical heating, you can now go from, let's say, dynamic operations that takes maybe hours to days to maybe seconds. And the general concept is that you now have a Joule-heated system where you are providing the endothermic, say, where you are overcoming the endothermicity of the reaction
by providing the heat with an electrical source, and then you couple that to whatever absorption or pressure swing absorption system you would like to use. But how exactly? So the general objective of this project was to do this sort of feasibility study of the proof of concept. With that, we wanted to have something that was dynamic on and off, electrically driven, compact, and selective, and that could be stable over time. Now, to develop this, we have to go to the basics. So if you look at the reaction scheme of the ammonia cracking, you see that the first thing that happens is ammonia absorption. And in this process, it is well known that the nitrogen-hydrogen bond dissociation is a rate limiting step at high temperatures. But if you are working at low temperatures, then it's a nitrogen-nitrogen bond recombination, the rate limiting step. Essentially, the surface is covered by nitrogen, and now you are sort of nitrogen inhibited, not poison, as it was mentioned earlier. And at high temperatures, it's actually the nitrogen-hydrogen bond dissociation. So the underlying question that we have for this project was, can we actually go back and forth between these two rate limiting steps in such a way that we can enhance the overall reaction rate? So this is not a concept that I invented. It's actually something that was is well known in the catalysis community for many, many years. But more recently has been at the University of Minnesota, sort of brought up again to life these dynamic or oscillation frequencies for catalytic conversion. The general idea is you have a reaction energy diagram where you are operating at temperatures where these, let's say, is your highest activation varies the nitrogen-hydrogen bond dissociation. You can actually go from that to a condition where your nitrogen-nitrogen bond is, distortion or nitrogen-nitrogen bond formation is the rate limiting step. And so by moving this molecule here to this side and then moving it up by changing this energetic energy landscape, you could potentially use it as a ratchet. Yeah, so you can actually bring in the ammonia, break it, form the nitrogen species, and then desorb that, let's say, almost like a concerto type of process. Yeah? So that you bring molecules that go from one and then the other. That only happens when you reach that sort of optimal oscillation frequency. That is explained by this, let's say, cartoon here about the changes in the delta H. So we use that concept and we thought, okay, how we can use a very fast way of oscillating from one state to another in a very, very fast way. So for that, we actually came up with this design that you see here, where we have essentially two electrical leads that are in contact with this material that is underneath. This is a reaction chamber where the gases are coming in from one side of the reactor and then they exit. And inside this volume, we have essentially a graphitic material where the heat is generated by flowing a current. And at the surface of this graphitic material, we have a nickel catalyst that activates the ammonia. So this reactor design essentially helps you to provide heat very, very fast. And here we can look at the temperature locally at the surface of the catalyst using a pyrometer in the order of fractions of hundreds of milliseconds. The reactor looks like this. As you see in the picture, we have a window to see through with the pyro probe. And here is the reaction chamber with the two inlets. This is the face of this side of the reactor, and this is the bottom part where we have a refrigerating coolant just to ensure that we can do dynamic operation. Now, the system, when you look at this, is the surface of the graphitic material that we use as a heater. Is based on pyrolytic graphitic sheets. This is how it looks after the nickel coating. The nickel coating is very thin, it's only about 50 nanometers. And this nickel coating is not an optimum catalyst, but it's just sufficiently active to break ammonia. We know from the catalysis point of view, the best or optimum size is something about 2 to 3 nanometers, where you have these B25 sites that activate the ammonia very easily. So this is by far the best catalyst ever. So let's keep that in mind. So this is how this process works. So we provide electrical pulses that are very, very short and very, very large, sufficiently large to reach, let's say, in 8 milliseconds. We go from 200 to 800 degrees C, that's 75,000 degrees C per second. And we cool down at a rate of 1,500 degrees C per second. That takes about 400 milliseconds to cool down back to 200 degrees C. So then what we do is that we calculate the integral temperature average of this system, and that's about 300 degrees C. This is a very important detail for you to keep in mind. So we start running this at 1 Hertz. So we send a pulse every second, and we look at with a mass spec what happens with the ammonia. And this is what it's. So when you have the system off, nothing happens. There is no ammonia breakup. There is no hydrogen. And the moment we just turn it on, all of a sudden you see ammonia conversion. We get about 5% conversion at 293 degrees C. You might wonder, what exactly does this mean in the context of ammonia cracking? Well, we can calculate a turnover frequency assuming the geometrical area of nickel that is available for this reaction. And based on that, we can estimate the turnover frequencies. So what we have done to benchmark these results is that we have a separate plug flow reactor where we have tested nickel-based catalysts on alumina. And these are the typical turnover frequencies that we get that are actually in line with a lot of the literature. And you get values that are, you see here, at 0.06 seconds to the -1 at 500 degrees C. Now, when we look at our material, this is the turnover frequency that we get. We get about 20 seconds to the -1 turnovers at 292 degrees C, and that actually resembles the activity of a nickel-based catalyst at 800 degrees C. So this is a sort of a very, let's say, a unique way of activating the nitrogen molecules, in this case, the ammonia molecules, a much lower average. A fundamental question, of course, is how can this respond to changes in the frequency and the temperature? Maybe I don't have time, by the way, to go through all of this. But one of the things that we can do is we can vary the frequency at which we send the pulses. The consequence of this is that the total temperature, the average temperature actually goes up because now you don't have enough time to cool off the system before the next pulse comes in. And what we can do is that we can see what is the effect of the amplitude on and also the average temperature on our kinetics. And so in principle, you expect that the higher the temperature, the better the performance. That's the general rule. And if that was the case, then everything that, if I write down using, transition state treatments, the reaction rate expression for this process, it boils down to this rate equation that you have here. Assume that reversibility is not such an issue. And you see here that this term, this is essentially your Arrhenius equation or Arrhenius term, should increase the higher the temperature goes. And so if that is true, then the reaction will be exclusively controlled by how high I go in the peak. And so I can assume that this is a typical activation variant, and I can see what is the value of that exponential term. So this is essentially my kinetic constant as a function of the different frequencies I use. And what you see, generally speaking, this number actually starts to go up as you go in higher and higher temperatures. So the calculated rate actually should go higher and higher and higher as I go to these higher average temperatures. But in reality, when we calculate the turnover frequency that we measure experimentally, we see a very different picture. What you see is that the turnover frequency actually decreases as you go with faster frequencies. That's a very counterintuitive effect. You don't expect that the rate will decrease with the increase in temperature. Now, what this means is that there might be something else that is playing against us during this process. And what you see actually is that there is an optimal frequency at which this process is enhanced to the maximum. That's when you reach this very high. It's now 35 seconds to the -1. And so for that, we actually had to do quite a few kinetic experiments. But let's say, generally speaking, if you look at this reaction order, apparent reaction order on ammonia, the lower the temperature of the maxima that we apply, the lower the order. So that would suggest saturation kinetics, which makes sense. Lower temperature, things stick longer on the surface. Higher temperature, things do not stick so well. But the one that is intriguing is the hydrogen, because that gives you the opposite. What you see here is that there is more inhibition when you have the higher temperature. So that suggests that the moment in which you are going to higher temperatures, you're sort of trying to get rid of the hydrogen that is on the surface, and that helps you to accelerate the reaction kinetics at the higher, let's say, peaks during this pulsation process. But that would be, let's say, very counterintuitive otherwise in an isothermal process. So obviously, the conclusion from this is that this maxima is linked to the surface coverage fluctuations during these peak temperature swings, rather than just your Arrhenius effects. In conclusion from this second part, and the message that I want you to take home is that we can achieve very high reaction rates with this rapid switching. There seems to be a 1,000-fold increase in activity when we are at this kind of sweet spot of 2 Hertz. We still don't know exactly why that is. We think that it has to do with the surface coverage. We're doing more calculations to prove that. Yeah, so what is related to this one. And so it's, let's say, conclusion. I mean, this is something that we're really looking forward to see how further we can take it. Having said that, I want to thank also and give acknowledgement to all the PhD students and let's say especially the research collaborators that help us to kind of polish these ideas, and of course the funding agencies listed in this figure. And finally, before I let you go, I wanted to do a bit of promotion or so for the postdocs that might be in the audience or PhD candidates. I don't know if we have any PhD candidates, but let's say PhD. Let's say people, but I'm the project coordinator of this national program on hydrogen and green electrons for nitrogen-based chemistry. We're looking at nitrogen-hydrogen, nitrogen-carbon, nitrogen-oxygen bond chemistry. We're going to have something like 20 PhD, 20 postdoc positions in the whole Netherlands. And so if you know, or if you are interested in knowing more about it, please just let me know. With that, thank you very much.
Thank you very much. In this presentation, I have a suggestion with some experience dealing with the European Commission. This is wrong, and they will tell you. This is Horizon Europe, and they will make you change all the deliverables. So change now. We got in a project, so be aware that you have to change. So questions for Jimmy? Yes.
Professor Albanese, thank you very much for your presentation. I'm Gaetano from Eindhoven University. For my PhD, I was working on ammonia synthesis, ammonia decomposition, and back then, when Kamel and Fausto wrote the proposal of my project, the hydrides and nitrides were the most interesting materials for these processes in terms of activity. But then, of course, we came to know that they are very unstable and difficult to scale up. So we moved to other solutions. But I never thought about these oxonitrides that you were mentioning. Can you share some information with us about how they really work, about the mechanism that is happening? Because I think that in slide 14 or 15, you were showing a comparison with nitrides and oxonitrides.
Yeah.
They work even better. So.
So the data presented it's on these mixed things. We don't know exactly what the phase, crystalline phase that you have there. That's what we are, let's say, working on right now. There seems to be, you have 2 possibilities when you are making these materials. You could have a metal nitride that has oxygen, so that would be an oxonitride, but you could have the other one that is a metal oxide that has nitrogen on it. And they are very different, crystallographically speaking, and also chemically speaking. They will have very different behavior. The data I'm showing you, we honestly don't know yet. I don't dare to tell you it's one or the other at this moment because we don't know. But this is, let's say, we're not the only ones that have thought of coming up with ways to stabilize these metal nitrates. There's actually a very recent paper in Angewandte Chemie from Ozono's group where they also exposed it to water and they did kind of, let's say, all dirty tricks to see if the catalyst was dead, and they show that it's still active. And it is because you put something that has oxygen resistance on it. They dope it with aluminium in that case to make it more stable. So in short, you can have either one of the two. To be, let's say, conservative, I don't dare to tell you what exactly is working so well with ours, but hopefully when the PhD students publish their work, we will disseminate the results.
There is a question online for you. If you are using pure ammonia, and how you measure the order for the other gases, hydrogen, for example.
Yeah, so for the ammonia cracking, we feed ammonia into argon, and the concentration of ammonia is 10% in argon. We don't apply any special, let's say, treatment. It's a bottle that it's a synthetic mixture. Mm-hmm. So we don't expect traces or so of water into the line.
Yeah, but I think the question is also the reaction order. I guess you have to do also more experiment with other concentration to know the reaction order.
Yeah, so we dilute in argon. That's what we do. So that's how we vary the pressure. So we have a 10% bottle, and then we just go down, 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 down. But we haven't done the, let's say, higher concentrations because for safety, we cannot just have a pure ammonia bottle in this setup. We'll have it for the other ones, but not on this one.
Other questions for Jimmy?
Thank you for the nice presentation. I was wondering, because I understood that in the project you have also structured catalysts, okay? So you're gonna use this catalyst code on the structured, let's say, catalyst, but did you try already to do that? And how you're gonna code this structured catalyst?
Right, so currently the plan is to explore both, either just having a pelletized form of our material in combination with the structured, essentially a heat transfer mesh, yeah, or coating the mesh. Yeah, so the coating of the mesh, it's something that Umicore is expert on. So what we plan to do is just to pass on them the powders, and they will have to create the slurries to do this. So recipe development and so on. So I cannot tell you because it's really at Umicore's side, but from our end, that's the idea. We will start first with pellets and the mesh and compare that to coated mesh.
Yeah. No other. Oh, yes. Thank
you, Julie, for the nice presentation. I was wondering, are you also going to do some research on the stability of the catalyst because you're doing a lot of pulsing? So that would be a kind of a bottleneck when you try to scale up.
For the dynamic operation of any of these processes, the stability is a major issue. Temperature swings and things like this, they turn to lead to sintering and so on. So the short answer is yes. It's one of the fundamental questions we have to address if we want to have a scalability of the process. In terms of current state of the project, I don't have data about stability. But it's part of the research plan.
Okay, so in view of time, thank you, Jim, again for that presentation. And I will try to take the presentation of Antonio. Was it a PDF? No. I see it. Share the screen. Okay, so now we have the last presentation of today. Of the workshop is a very short presentation from Dr. Vita, who is the head of the pure process material and technologies research team at CNR, which is the National Research Center in Italy, and he has a lot of experience on heterogeneous catalysis from powders to structured catalysts. And it's also a pleasure to work in many projects with the catalyst from Antonio. So Antonio, please.
Thank you so much, Froso, for this kind introduction.
Yeah.
The promise of green ammonia, many things are just said about this. The promise of green ammonia about carbon-free energy carrier for a sustainable future. I can add nothing on this, but I would like to focus on some drawback. Especially when we think to produce green ammonia from renewable energy source, and we have to think to downsize probably the system, the complete system. We have to think also that we have to eliminate completely. Here is very little, but it's a big steam reformer plant integrated with our Bosch system that feed hydrogen, nitrogen, and heat. Integrated the heat for the fish panel efficiency for large scale production of ammonia. Eliminating this with the electrolysis system. Maybe we have some problems related in principle about cost, capex, but also on energy demand. To overall energy demand for the global system could be also another problem. This because I absolutely agree with Jim. We have the same image. When we downsize, other Bosch projects we go, probably we meet some problems related to energy consumptions. The energy consumption increase because there is not much heat that comes from a conventional steam reforming plant. So we have to think to new solution. We need to develop new kind of catalyst, new kind of reactor that can work in mild operating condition at low pressure, low temperature, and that's and similar for ammonia decomposition. Actually, most ammonia cracking technologies are based on the existing steam methane reforming technology. We have a reactor, heated reactor, an absorber then, and a PSI for the purification at the end. The process is based of high temperature. It's a high temperature process, 809 degrees, to obtain total conversion of ammonia. So also in this case, the intensification of process is a way to reduce temperature, reduce pressure, and to realize more efficient process. That's why there are many European projects, international projects that go in that direction. And here we have a demonstration of this kind of process. I'm involved in ammonia, in other projects, ammonia malt-based hydrogen storage for Europe that was produced by Angela. It's not our coordinator. Our research team is involved in this project to develop structured catalyst, specifically gravity-based. They extract some structured support 3D printed that should be integrated with ammonia, with membrane, carbon-based membrane. And in Andrea project, we have a similar concept for hydrogen production from ammonia decomposition. Also in this case, we are involved to develop structured catalyst, 3D printed basket, and catalyst to improve also in this project, heat and mass transfer to work at low temperature. In case of ammonia, synthesis to work also at low pressure. So this presentation is based, it's a summary of the activity of our teams on carried out to develop this kind of structured catalyst. When we talk of structured catalyst, more or less these are all the steps involved in the preparation of this kind of structure, the POX, the periodical overcellular structure, catalyst synthesis, support manufacturing, and all the steps, substrate pretreatment, slurry preparation, coating, and so on. These are all the steps involved in the preparation of the structural catalyst. And on the right, you can see the principal equipment that we used during this activity and the project. We used plant carbon milling to reduce the size of the powder. We did the rheological study on the slurry preparation. We used the spin coater for the distribution of slurry on this catalyst. So everything starts with the design of this structure using the software. Then the other steps is printing using the powder, metal powder, and printing. And additive manufacturing in general give us the possibility to work with different materials, depending on the process, depending if you need some specific conductivity, thermal conductivity of materials, depending on the temperature of application. So we can print nickel-based, copper-based, aluminum-based materials easily in different form, in different geometry, and we have with the design and with additive manufacturing, we have the possibility to manage virtually everything, manage the dimension of cell, the unit of cell, the sheet size. We can decide also the porosity of materials. We can decide, can manage also the surface area, the specific surface area, in order to print with the desired material, the desired support that we need, but with that specific process, that specific catalyst also. But what we manage is the cell size, the pore size, regulate the dimension of the pore, the sheet size that regulate the thickness of the wall of the other structure. Everything can be modified during the design of the structure. In this case, we have a particular type of periodical open cellular structure that are named triply periodical minimum phase microarchitecture in different geometry, cuboid, diamond, EWP. We can plan everything, we can design everything, and at the end, we can decide, we can manage a lot of typology of structure that can be of support that we can use for our application. So if you look at the first column, we can have different porosity, and especially we can have different specific surface area, just changing cell size, pore size, and sheet size. Everything influences, for example, the pressure drops, and I will see something after. One point. So it's true, we can design everything on the paper, on the software. We can, but then we need to know exactly what we can do with our printer. We know, of course, there are some limitations, physical limitation, drop the structure during the printing process. during the powder bed fusion process. So here we have an example what's happening. This laser beam is your wire, your wire. Of course, you can see the difference on morphology of the gyroid that is completely different. In this case, we improved everything. And with this page, we are able to print a gyroid with this characteristic, with 0.3 millimeter of sheet size, 3 millimeter of unit cell, and obtaining all the other parameters. Another thing that we can do is a polish technique we can use. Sandblasted is a technique that used in additive manufacturing to completely remove everything and obtain a almost flat surface. But this is not our choice because for coding, we experience some problems, and it's better to have something like this, something that has width. It's called this as width. Because we generate a lot of anchoring points, and this is very good for the stability of the coating system. So, of course, sandblasted are at a cost, important cost, because manufacturing for this structure isn't a cost for the production. Sandblasted is an operation more as a cost. But we can conclude that, for example, this kind of BCC, it's better to have a structure like this. You can make some sonication to eliminate all the residual particles that are weakly bound, and then you can go with your coating. Coming back to what I said before, changing the characteristic of the structure means also changing the pressure drops in your reactor. In this case, when you increase the porosity, it's a specific surface area, your pressure drop decrease. And so also in this case, we have 1,000 possibility to manage your support. Gyroid is another kind of structure support we can print. Also in this case, you can see if you increase the cell diameter, the unit cell, you modify the sheet size, you can obtain different structures with different porosity that can be used for different applications, from coating to packing, for example. And also in this case, if you do this, we have different gyroid, almost constant there, but different porosity, and of course with different pressure drops increase when you reduce the porosity of your system. Everything can be decided during the design. Another sample, here we have a comparison between all the three different kind of geometry, BCC, Kelvin, and gyroid. As you can see, BCC, that is something that reminds the monolith, like a monolith. So a very, very, very low pressure of the And inside Humber, we did also in collaboration with QE and NG, with some experiment playing on CFD, some model that confirmed that is a good agreement experimental and theoretical results. Another interesting finding is something that is related on thermal conductivity on heat transfer coefficient at the end of the experiments. Geoids seems to have a better situation respect the other two in terms of balance between pressure drops and heat transfer coefficient. So coming back to the coating methodology, develop a deep thin coating method. It's not so complicated. It's very scalable method that in which we prepare we need a thermal treatment initial of our super in order to generate some oxide on surface that help the bonding the stability of catalyst, and in parallel we prepare a slurry, a special composition using some binder, some discordant, this is some that is glycerol water and a solid amount, and then we make some two kind of operation. One is a dipping, and the other one is a spinning in order to get through out from the support the excess of slurry. Then we recover also the slurry that we get out from the support, and then at the final calcination we repeat of course once. We see depending on the time, 6 times of time, depending on the amount of catalyst we need to load. More or less, this is more or less a maximum value we can reach about 0.0 to 25 grams per cubic centimeter in order to avoid occlusion or clogging phenomena. A final calcination, after a final calcination, we obtain a stable structure of the catalyst. Of course, I can go deeply in all that we did. A number of parameter influence, slurry preparation, slurry rheology, stability, typology of catalyst, everything was studied inside Amber, inside Andrea project. And what we do in Amber, also in Andrea, we are doing a scale up from very little pieces. We start with these pieces. Then we had an intermediate scale up with larger pieces, and then a final scale up for the demonstration in which we activated the gyroid, the DCC support, are ready for integration with the membrane in a membrane reactor. Some other things about coating and about stability of the slurry. Initially, we had some problems to find exactly composition of the slurry. So it's fundamental in this. It's fundamental the rheological study in order to understand which is the rheology of the slurry that can change normally in from shear cleaning behavior to Newtonian behavior. Newtonian would be the best solution because a very stable slurry. Total shear cleaning can be used, and we did many. We tried different things: effect of figure, effect of water, amount of catalyst, and at the end, after mechanical stability test, we found a better solution, and we can say that a loss of material near the 10%, and this is acceptable for our structural catalyst. So for the scale up, we used similar equipment, just bigger. It's design. We design also a holder, the host the big pieces of box for inside our big spin coater. And so here we have a different kind of support we used with different kind of sites for at least for demonstration. For demonstration, we activated the support with 5 centimeters diameter, 10 centimeters in length, but also we activated support for single membrane reactor, single tube membrane reactor needle. And what we do was starting from little pieces and look at we was lucky in this case. We used the JM catalyst, developmental catalyst for the development inside the project. We was lucky during the scale-up because the rheology not change so much when you increase the amount of powder for the activation of bigger pieces. This is the ideal situation. So we used the same composition of slurry for the little pieces to bigger pieces. And these are the structural catalysts we obtain at the end. We have some image that demonstrate that the coating is very good. We have a homogeneous distribution, also with very complex gyroid structure of catalyst inside. Also inside, here you can see here the inner wall. The gyroid is the BCC, and the total amount of catalyst we loaded is about 54 grams of catalyst per in 27 grams of catalyst for each pieces of box. Another thing that we are exploring in number is a packing. In this case, the somatic prepared some similar catalyst with the required sites, fractions, positive fractions for packing. Actually, the best measure difference are that in this case we can charge 250 grams of catalyst against 50 grams with simple packing procedure, not so complicated. And we have established that structural gas integrated with membrane prepared by Technalia, integrated with a QE, and this is the reactor, and the activity is in progress, So we have no data actually on this, but basically this is the final configuration for a demonstration. You can see that in this case, a gyroid catalyst integrated with the four membrane. But I can give you some data on the single tube membrane reactor obtained with the second generation of catalyst. In this case, we have a structured catalyst 10 centimeter long in length, and if I remember well, it's 27 centimeter in diameter, integrated with one membrane in a single tube membrane reactor. Very quickly, some results that demonstrate how the membrane helps to obtain okay, yes, I go have to shift the equilibrium and in some situations, some cases that this is a favorable compromise. 100 degree, 40 bar, with a sweet gas support. We can obtain in promising activity for ammonia synthesis. Very quickly, same things for ammonia decomposition. This is an Andrea project. Very quickly, because the operation, the activities was very similar. The only thing that during the scale up, we got a problem with the catalyst prepared by Unitor, because the rheology was different. And so at intermediate point, we need to understand, to study the rheology, study the influence of UVA, study the influence of visceral, in order to reproduce the similar situation in rheology study, and to activate the second generation. And also with this composition, we obtain very good results for second generation of catalyst. And we are working on fifth generation. So this is the work that we have to do the next months, I think, to activate all these catalysts. About catalytic performance, I can give you some results on little POX in a microscale test facility. Is operative condition. So what we obtained is just the gyroid works a little bit better respect the other when we go to lower temperature, because the characteristics of gyroids are a support with high specific surface area, and has also a very interaction between a good interaction between the gas and the surface of gyroid. That is very complex. It's like a vortical system. And there is more interaction between gas and the catalyst distributed on the surface. So at the end, the lesson learned and on Amber and Andrea, that is additive manufacturing is a powerful tool to contribute to produce new configuration of catalytic reactor. The integration with membrane is something that can work, but need to be improved, of course, and especially we need to improve the selectivity of the membrane. But in general, there are interesting and promising results to go to follow the way. This is the team involved in the activity, and just you are welcome to participate in the conference we are organizing in Palermo. Thank you so much.
Thank you very much. Now we are used. That's why you are the last one in the list. So thank you very much. And as Antonio said, we have a conference. Actually, he is organizing a conference in Italy in August, at the end of August. Well, questions for Antonio? Yes, coming to you.
Thank you very much for the presentation. I was wondering about the comparison of the different geometries. So it's when you change the geometry and you look at the thermal conductivity, are you keeping constant the, let's say, metal fraction that you have?
Yes. The metal is constant.
All right.
It's the geometry that change.
Yeah.
So it's something that is related to the interaction of the gases with the surface.
Right. And the second question I have is, maybe I don't know if you have measured, let's say, these how exactly you measured it, but we know that the direction of the printed, I mean, you are using this laser melting powder, right? In that process, you sort of have a printed direction, and that creates an isotropic thermal conductivity because you have then crystals that grow in this, let's say, direction, and then you have, let's say, layer by layer. So these creates, that means that you have an interfacial or a boundary between one crystal that grew and the next layer that you print. So in general, you will have a higher thermal conductivity in the direction that you print. Well, I don't know how exactly they are printed, but it seems that based on what you're saying, is it printed from the bottom to the top. So have you tried to compare what is the thermal conductivity difference between radial versus
we use
axial?
to print to put from the top, from the bottom to the top, just only in that way, and actually no, we don't consider this thermal conductivity from I mean on modeling side. But in the reactor we measured this and we didn't see any kind of distance or difference. There is a good axial thermal conductivity and radial. So radial axial thermal conductivity. So at the end, in macroscopic system, we don't see problem related to the growing of the structure.
But I
It's
think
very depend on the material, but the conductivity is very active.
because my guess is that as you start, let's say, increase in dimensions, that these small differences will start playing a role.
So we can be more precise now that the campaign on bigger pieces are started. With the little pieces, we didn't see a low axial thermal conductivity respect the radial.
In any case, just to add to this, the biggest piece that Antonio showed for the Andrea project, so with the 7 membrane, is not much smaller than the biggest piece you will do in industry, because in any case you do multi-tube. So you have a lot of tubes with this SML. Yeah. And this has to do with indeed thermal conductivity, but also the difference in temperature on the different membranes. So you want them to work at the same temperature. So there is a maximum you want to go, and it's not much bigger than the 7 membrane piece that I'm finishing. Okay. Any other question? I think we are a bit tired because of the long day. So I want to, before closing, thank you, Antonio, again for that presentation. I want to say to the people online that obviously the presentation will be shared, and also the video will be shared. So everything will be on all the websites of the different projects. So you will get all of them. I want to introduce also Mirian, Frosi. Please come. It's not another presentation, don't worry. Miriam is from the municipality of Eindhoven. So when we speak about policymakers, it's always nice to have you here. Last time you gave a presentation, perhaps you can give a few words, but Miriam will stay later for the drinks, so you can discuss with her.
Welcome everybody. I'm happy to see you here in this beautiful city of Eindhoven. I'm a councillor at the city of Eindhoven. I'm also a party leader. And it happens that I'm also working for the Ministry of Infrastructure at the transition path towards sustainable roads. We also work with the TU University, with a lot of professors, and I do really believe in the strength of cooperation. Because I work with really, really clever people like you, all of you. And I do believe that you are in engineering because you really love searching for the solution of a problem. Everybody does. And in the end, the solution is there. And in the end, you also have really nice laws that can help you to implement this solution. But you do need, first of all, to cooperate. And in cooperation, what I see here, last time I could stay longer, but I have the feeling that here is the place to be, because without cooperation, you will never succeed in implementing innovation, in implementing the right solution for a better world. And yeah, I'm really happy. And I was outside, I was really laughing about the name Caipirinha. So I'm glad I can drink one with you later without alcohol, because I have to work tonight at the council. But once again, if you have time, enjoy Eindhoven. You also are really lucky because the sun is shining. It doesn't happen every time. Enjoy. There's many places to stay, to visit. It's the place where Philips started. So here is really an inspiring place because here the light was there. So we substitute the candles with this wonderful light. So enjoy again the stay. I promised that I was short, so I will stop, and after we can talk. And an applause to you, and keep on cooperating. Thank you. Thank you.
Thank you very much. And now I would like to call the coordinators, if they are all here, Jimmy, Konstantinos, Valentina, Ione, and Angela. Angela is in a meeting. Yeah, yes. You know, when you are a coordinator, you are always in a meeting. So I think join me to thank the coordinator. We have this kind of workshops and meetings because of the projects, because of the nice science that they do, and also the time that they take to disseminate the knowledge. Thank you very much. And then, of course, thank you also, Simone and Argus, for the organization. Thank you very much. And now we have some time for drinks. So enjoy the time, but also speak with each other. And we see each other next time. We always organize this kind of events. When we started with this particular one, we discussed with Jimmy in particular to make it at least every year. And then there will be probably new projects. Somebody's finishing in 2 months, but I'm sure that there will be more projects, and we will make everything possible to bring more projects. And perhaps we have also to rotate this, right? Not only Eindhoven is very nice, but also other cities and universities are nice. So thank